All right, welcome back to another calculus lecture. So this will be our last lecture of the summer. Hopefully you all have learned a lot and come to understand a lot of the important concepts in calculus. And for those of you continuing on to Calc 2, I wish you all the best. And of course, those who aren't taking Calc 2 also, I wish you the best of luck for all of those things that you plan to do in the future. It's been a very strange semester for me. Lecturing to a piece of paper and not seeing students' faces is quite different than lecturing in person. But anyways, so let's go ahead and crack on with our final lecture. So in the last lecture, we talked about doing or computing volumes by integrating cross-sectional areas of various different solids. And today what I want to talk about is another sort of method for computing volumes of objects that have a specific form. And these objects are typically called solids of revolution. So the idea is that, let's say I'm going to have a function like so, where, I don't know, I got one, so I've got some function like this between two points, and then what I'm going to do is take the area bounded by the curves, by the on this interval here, and bounded by this function in the x-axis, and I'm going to sort of sweep it around the x-axis. So you can imagine sort of sticking a piece of paper on a this is an eraser, not a piece of paper, but you can imagine sticking a piece of paper on a pen and then sort of spinning the pen in your hand, and the shape that appears in the air, that's the object that we're interested in. So in this case, it would be something like this. If I attempted to draw it, it would be this kind of circular or conical shape. And what I'm interested in is computing the volume of objects of this form. So there are going to be a few different methods that we use in order to compute these volumes, but overall it's sort of the same principle throughout. Okay, so maybe let's go ahead and start with the example that I mentioned last time. So let's compute the volume of a cone, not a pyramid, a cone of radius r and height h. Okay, so maybe before we do this, let's draw a picture. Imagine that I have my cone sitting on my desk with the circle part down and the tip sort of coming up like the kind of cup you get from a water dispenser at a dentist's office or a doctor's office or something. Imagine I have one of those sitting right here, and I'm just going to cut it straight down the middle. I'm going to take a vertical cross section straight through it. Well, what would that look like? It would look like a triangle. So the vertical cross section, and in fact it's an isosceles triangle, it would look something like this. If I continued to draw the base around, I'd have something like this, but essentially I have a triangle here. And so if I think about putting this line down the middle, if I want to translate it to thinking about objects of this form, then really what I have is something of this form, where I have my axis, I have my height, which is h, so this is going to be h right here, and then this I can think of, this vertical line right here, I can think of as the axis, and then this as a function where it's just going to come up to, it's going to start at the origin and just be the straight line connecting the point h comma r. And what I want to do is actually just sweep this around the x-axis. Okay? And I'd get something like this, and I get exactly a cone. Okay? So how do we actually do this? Well, we do it in the exact same way. We think of integrating cross sections. But now we're going to determine the area of those cross sections using the particular function that's given in our problem. So here, let's think about what function this line represents. Well, this is a line with y-intercept 0 and slope r, rise, divided by the run, which is h. So this is f of x equals x times the slope, r over h. Okay, you can see that if I plug in h, I just get r back out. Okay, so now what I want to do is think of, if I pick out a slice at x, what's going to be the area of the slice at x? So what is a of x? This area of this cross-sectional slice at x. Well, this, we just have circles and we're rotating around the x-axis. So this is something called the disk method. We're going to add up a bunch of disks here. So a of x in this case is equal to, well, pi times the radius squared. I have a circle and I want to compute the area of it, so it's pi r squared. But what is the radius here? The radius is precisely f of x. So this is just pi f of x squared. And in our case, that's going to be pi times x times r over h squared, which is just pi times r over h squared times x squared. Okay? So now we're ready to actually compute the volume of this thing. We're going to do exactly like we did the last time. We're going to integrate these cross sections as we move along the x-axis. So the volume is equal to the integral from 0 to h of pi r over h squared times x squared dx. All of this out front is just a constant, so we'll pull that out. Integral from 0 to h of x squared dx. And actually, this is a very familiar integral. We did this integral last time. This is just going to be pi r over h squared. We integrate the x squared, it becomes 1/3 x cubed. The 0 here isn't going to matter, and so we just plug in the h, and we're going to get h cubed times 1/3. And so we get pi over 3 r squared times h. Okay, it actually looks very similar to the formula for the volume of a square pyramid. We had the s squared times h when we had a square base. Now we have an r squared, but like a pi. So the pi r squared is like the area of the base, and then we're dividing by sort of the number of dimensions we have. Not necessarily the right way to think about it, but just an observation. Okay, so this is an illustration of the disk method. So let's go ahead and actually just write that down so that we have that in our notes to refer to. So, theorem. This is the disk method. So let f of x be a function which is positive, so we're not going to deal with functions which cross the x-axis. We're only going to deal with functions that have a graph that is completely above the x-axis. That just is what it means to be a positive function. And then this is going to be for x in the interval a to b. This little e sign just means x is an element of this interval. The volume, I don't know if you all can hear that cricket outside my window. It's very obnoxious. But I apologize for that. The volume V of the solid created by rotating, let's just spell that again, rotating the area under the graph of f of x between these 2 points, between x equals a and x equals b, around the x-axis So we're specifically rotating around the x-axis. We could have rotated around the y-axis, and we'll have an example of that, but we'll need a different method for it. But here we're going to rotate around the x-axis. This volume is the integral from a to b of pi f of x squared dx, exactly the integral that we wrote down before. And exactly what we're doing is just integrating these cross sections, which are circles. We have pi times r squared, the radius squared. So we're computing the area of a circle here, and then we're letting that radius depend on x. And so as we move along the x-axis, the area of our circle is going to change, but all we're doing is just adding up all those cross sections and then getting a final volume out at the end. Okay? So this is the disk method. The next thing that I want to talk about is something that we'll call the washer method, and it's really just the disk method, but in the same sort of form. We just do one extra step. So let's go ahead and try and motivate this with an example. So we're going to compute the volume of the solid created by rotating the area between the graphs of, and we're going to do two functions now, so f of x equals the square root of sine of x, and g of x is going to be the square root of cosine of x. Between, and the 2 points we're going to use are x equals pi over 4 and x equals pi over 2. And we're going to rotate that around the x-axis. So with these problems, as you might have already guessed, it is very helpful to draw a picture if possible. In this case, we can sort of do that, or at least get a rough idea of what we're looking at. So I'll draw the picture over here. So here's going to be pi over 2. Here's pi over 4. And now I just want to think about what these functions do at each of those points. Sine and cosine agree at pi over 4, and they evaluate to something like the square root of 2 over 2. So we'll just put that point in there, and we'll just say that that's where that is. We won't specify a specific sort of numerical value for it. It's not really important, yet at least. Now pi over 2, cosine of pi over 2 is 0. And we know what the graph of cosine looks like, and taking its square root doesn't change it all too much. So the graph of that is going to look roughly like that. So this is g of x. And then sine of x, the square root of sine of x, well, sine of pi over 2 is 1, and the square root of 1 is just 1. So 1 is going to be somewhere up here. Well, maybe we'll put it right there. And I want to sweep this around the x-axis. And the functions that we only care about between pi over 4 and pi over 2, so we'll just content ourselves with this guy. Now let's think about what happens when we rotate this. If we want to get a rough sketch, then I have this sort of ring outside, and then I have the rest of this. Just going to do something like this. And then I have this sort of inner like wedge that's actually what's called an annulus. So I have this sort of washer. That's typically the name we ascribe to it. It's a circle with a smaller circle taken out of it. So it's two concentric circles is what we call that. So we need to compute the area of this cross section. So again, what is a of x? Well, it's the difference between the areas of these two circles. It's the difference between two circular areas. This is going to be very difficult to look at later on in the notes, but if you've watched the video and seen me draw it, hopefully it was clear what I was actually trying to draw with this. F of x is this top function here. Okay, so how do I compute these circular areas? Well, I have my bigger circle, which is f of x on the outside. So bigger area is pi times f of x squared, and a smaller area is just with g of x, so g of x squared. Put those in parentheses just to avoid ambiguity. So if I want to compute the area of this sort of annulus here, these concentric circles, all I do is just take my bigger area and subtract away the smaller one, right? That's exactly what we're doing. We have this big area right here, and then we remove the smaller area inside. So, thus, a of x is equal to pi. We can factor out a pi from this. This is going to be f of x squared minus g of x squared, where f of x is the outside function and g of x is the inside function. So, let's go ahead and actually just compute this. So the integral, so volume now, we're ready to integrate. So we've got our area function, we've got our interval from pi over 4 to pi over 2. This is the integral, pi over 4 to pi over 2 of pi times, now we'll go ahead and plug in f of x and g of x. So this is going to be the square root of sine of x, but squared. So this is just going to be sine of x minus cosine of x dx. And now we just perform the integration. So we have a pi. Sine of x integrates to negative cosine of x. The antiderivative of sine of x is negative cosine of x. The antiderivative of cosine of x is just sine of x. And then we evaluate that on pi over 4 to pi over 2. And what do we get? There's going to be a negative cosine of pi over 2 minus sine of pi over 2, and then negative cosine of pi over 4 minus sine of pi over 4. And I'm running out of room, but hopefully should be all good here. So negative cosine of pi over 2, that's just 0. So this is 0. Sine of pi over 2 is 1, so minus 1. I have minus negative cosine of pi over 4 is negative square root of 2 over 2. Sine of pi over 4 is square root of 2 over 2 as well. So what do we actually have here? This is 2 times the square root of 2 over 2. And then I have a negative here multiplying each of these negatives, so I end up with pi times the square root of 2 minus 1. Okay? And we've computed the volume of this very strange sort of object that we get by rotating this area around the x-axis. You can think of this sort of as like maybe a bowl that's sort of sitting on a table. If you sort of took this and then put it on a table, you'd have like a bowl shape. I don't know. It's really kind of difficult to visualize these things sometimes. But anyways, even though it's difficult to visualize them, we can still compute the volume in this manner. Okay? So let's go ahead and summarize this with the washer method. So we'll just write it down. Whoop. And you can look at the notes 26 if you want to see some better diagrams or more refined versions of the ones I've drawn here. This is the washer method. So let f of x, now we're actually just going to require that it's bigger than g of x. so that their difference is positive. Their difference is bigger than 0. So for x in the interval a to b, the volume V of the solid created by rotating the area bounded between the graphs of f of x and g of x between x equals a and x equals b. Around the x-axis, these are very long to state, around the x-axis is just what we had before, the integral from a to b, pi, and then I do a difference of the radii squared. So the outside function, the bigger one, minus the smaller one, the squares of these, that is. Okay, so again, let's think about what this integral represents. We're taking cross sections, which are circles, this pi times r squared, but now we're going to take from a bigger circle and we're going to remove a smaller circle inside of it, and then we're going to be left with a pair of concentric circles, which are going to represent an annulus, and then that area, that cross-sectional area, is what we're going to integrate from a to b in order to get our volume. Okay, so this is the washer method, another method for solving these sorts of problems. The last method is sometimes called the shell method, but it's for typically when the washer or the disk method aren't really going to work. So I think the best way to sort of motivate this is with a sort of classic example of when you have to use this method. So let's compute the volume of the solid created by rotating the area under the graph of f of x equals sine of x squared, where x squared is inside the sign, between 0, x equals 0, and x equals the square root of pi, and this time we're going to rotate it around the y-axis. Okay, so let's draw a picture just to try and get an idea of what we're dealing with here. So here's 0, here's square root of pi, there's negative square root of pi. The graph of sine of x squared, you can put this into Wolfram Alpha or something, but the basic picture looks something like this. And then what I want to do is actually just take this area and sweep it around the y-axis. So the other sort of part of this would be over here, and the shape would look something like this. Okay? So if I want to think about doing this with the shell or the washer method, and in particular with the washer method is what we're going to have to do. I said shell a moment ago. The disk method or the washer method. If I want to do this with the washer method, I have to have sort of my outer and inner radii. And already I'm going to have to sort of integrate along the y-axis instead of the x-axis. And my outer radii and my outer radius and my inner radius are controlled by the same function. So, and if I want to integrate on the y-axis, I have to like invert this function, figure out like, you know, what sort of, how could I integrate the inverse of this? And it gets really unpleasant to think about very quickly. So what we're going to do instead is, instead of integrating these disks or these washers, what we're actually going to do is pick out a slice like this at x, and we're going to look at the cylinder created by rotating that guy through, or sort of around the y-axis. And then what we can do is integrate as these cylinders get sort of move along the x-axis. So you can think of like stacking bigger and bigger cylinders. I'm really trying to do this motion with my hands, and it's quite difficult. You sort of stacking these cylinders, these shells, inside of one another as you move along the x-axis, and eventually you assemble this whole thing. If you imagine the sort of Russian doll sets, what you're doing is you're sort of putting one sort of bigger and bigger outside on the other and moving out. Okay? So, in order to do this, we need to compute the surface area of this cylinder. We need to know what the surface area of this thing is, this is sort of our cross-sectional area. So what is A of x? Well, now A of x is the surface area of a cylinder with radius x and height. Well, what is the height of the cylinder? It's precisely f of x. Well, what is the surface area of a cylinder? Well, we can think about, in one lecture, I forget which lecture it was in, I think it was in the one of the applied optimization or related rates lectures, but we actually looked at the surface area of a cylinder. So if I have a cylinder here, and I sort of imagine cutting it and unfolding it, trying my best to draw this, then really the surface area is just the height times the circumference. It's the area of this rectangle, and that the rectangle has height, in this case f of x, and then the circumference is going to be 2 pi times x times the radius here. The radius is x, and so to compute the circumference you do 2 pi times the radius, and that gives you the circumference here. So A of x is equal to the circumference, so 2 pi times x, times the height, which is f of x. Notice I haven't squared anything now. Okay? So, and it's important to note this, we're not doing what we were doing before. We're not computing the area of circles, we're computing the surface area of these cylinders, of these infinitesimally thin cylinders. Okay? But notice what this actually does. It introduces another factor of x, which we really hoped we would get because we have an x squared in here, and now we can do an integration by substitution. So let's go ahead and compute the volume. The volume is equal to the integral. I'm going to integrate from 0 to the square root of pi. I have 2 pi x times f of x, so sine of x squared dx. Now we can do our change of variables, and really the one that we want to do is letting our u be x squared, because it's inside of sine of x, and its derivative, 2x, appears elsewhere in the integral. So if we let u equal x squared, then du, the new differential, is 2x dx. And then u of 0 is 0. U of square root of pi is pi. And so we can change our integral then into the integral from 0 to pi. So our new limits of integration, 0 and pi. My sine of x squared becomes just sine of u, and there's also a factor of pi right here, so pi sine of u. And then 2x dx, that's my new differential, so now this is just du. And this is an integral we can certainly compute. This is pi times negative cosine of u, evaluated from 0 to pi, and this is pi times negative cosine of pi minus cosine of 0. I'm sorry, it's minus a negative cosine, because I have a negative out front here, so it's minus a negative cosine of 0. And so I have a minus, which is a plus. Cosine of 0 is 1. Cosine of pi is negative 1, so I have negative 1 times a negative. So I'm going to get a positive 1 here and a positive 1 here, and then I add those together, and my final answer is, in fact, 2 pi. Okay? And so, now, with this, we can write down the theorem, which is going to be the last thing we write down in this course. A theorem, which is the shell method. So theorem, shell method. So we're going to let f of x be greater than or equal to 0 for x in a to b. And we're also going to require that a is positive because we're rotating around the y-axis in this problem, and so we really don't want to have to deal with a case where part of the area is on the left of the axis and part of it's on the right. It gets kind of annoying to do that. So where a is greater than or equal to 0, the volume v of the solid created by rotating the area under the graph of f of x between x equals a and x equals b, and we're going to rotate this around the y-axis, is, and we do the integral from a to b, the integral of the surface area of these cylindrical shells. So 2 pi x, the circumference of the circle, which is defining this cylinder, and then we multiply by the height to get the total surface area, so f of x dx. And that is the shell method. So if you want to compute these volumes, instead of using disks or washers, you want to use shells. Sometimes it's more convenient computationally to get this extra factor of x like we just saw, because then you can do a u substitution to actually compute the integral. Sometimes this is more convenient. And in a lot of problems, you can actually use several of these methods and get the same answer. There's not one that's always right, but there are some which are more computationally convenient. In particular, the shell method, when you need to get this extra factor of x and do a u substitution, it really helps to get that out. But sometimes it doesn't, and then you would use the disk or the washer method. Okay? So that's it for this lecture, and that's it for this course. So I hope you all have learned a lot and hopefully enjoyed these lectures. I've tried to keep them lively and not super dull, include a few meme references here and then. But anyways, yeah, so have a good rest of your summer, and I wish you all the best with the fall coming up. A lot of uncertainty there, but yeah, hope you all do well with that.